Hey there everyone, welcome back to another video. Today we'll be looking at the particulate nature of matter. Alright, let's begin. So numerous substances exist around us which we can see, touch, feel and smell. Other things like air are not seen by the naked eye, but we feel or see their effect on our surroundings. Thus, everything in the matter has a chemical connection and referred to as matter. What is matter? Matter is anything that occupies space and has mass. Nature of matter. Matter is made up of tiny particles called atoms. When atoms of the same kind are combined, the substance formed is called an element. Alright, let me give you an example. Let's say we have atom A, atom A, atom A. These are atoms of the similar atoms, and when they are combined together, they form element A. That's what it's talking about. Elements, examples of elements, we have carbon, we have iron, we have sulfur, and as of now we know about 109 elements, out of which 90 are naturally occurring and around 19 can be made artificial. When atoms of different elements are combined with one another, a substance called a compound is formed. Let's say we have atom A, atom B, atom C, atom D. This will form a compound with a different name. Let's name it compound X. And this element and compound are together called substances. Let's look at states of matter. We all know we have three states of matter. We have solid, liquid and gas. In solids, we have ordered and dense. They are ordered and dense. Liquids are disordered and usually less dense. Gases are very disordered and have much lower density than solid and liquid. Definite shape and volume. Definite volume but takes the shape of the container. No definite shape or volume. Very slightly compressible. They are slightly compressible and then they are highly compressible. Moving on to solids. Solids have a definite shape and volume and can only change their shape by force or when broken or cut. These particles are packed closely together, as we saw. These are how closely packed the particles in solids are. They are normally hard and rigid, high density, incompressible. The particles cannot move freely but can only vibrate in a fixed position. In crystalline solids, the particles are packed in a regularly ordered repeating pattern. This pattern is called a lattice or lattice. Solids can be transformed into liquids by melting, and liquids can be transferred into solids by freezing. Solids can also change directly to gases through the process of sublimation, and gases can turn directly into solids through the process of desublimation or deposition, or deposition as some people like to call it. Then we have liquid, definite volume but no shape, takes the shape of a container, high density, less than solids obviously, slightly compressible, occur in cluster with molecules slightly further apart compared to solids. They are free to move about within a confined vessel. They slide past each other, as we call it, slide past each. Their molecules slide past each other. Then we have gases, no fixed volume and no fixed shape. It's compressible, low density, far apart, one molecule. So how the molecules are far apart, moving at high speed, randomly, and very negligible force of attraction between them. So random motion of their particles. And a liquid may be converted to a gas by heating to its boiling point. That is that. We just looked at this table, but if you want to read it, I'll let you go down, pause and read. It's the same thing but a little more detail. And yes, you need to read the table. I will not waste much time on it as we have to finish this fast. Alright, back. Now physical changes. There are changes in state, or physical change in state are changes in which no new substance is formed. For example, an ice cube or dissolving salt in water. When I melt an ice cube, I can freeze it again to get an ice cube. Physical changes are reversible. For instance, yes, I just said this. Changing the state of a matter as a physical change, and it is either done by heating it or cooling it. The following diagram represents change in state. So from a solid to a liquid we have melting, liquid to a solid we have solidification or freezing in simple words. Then from a solid to a gas directly is sublimation, gas to a solid is deposition or desublimation, a gas to a liquid is condensation, a liquid to a gas is evaporation or boiling. Then next up first we have melting. Melting is when a solid changes to a liquid. It requires heat energy which transforms into kinetic energy, allowing the particles to move. It occurs at a specific temperature known as the melting point, which is unique to each pure solid. Melting point, melting point is the same as freezing point. Remember that. Then we have boiling. Now you must know the difference between boiling and evaporation. Boiling is when liquid changes to gas, requires heat which causes bubbles to form below. They have made a board below the surface of a liquid, allowing for liquid particles to escape from the surface and within the liquid. Occurs at a specific temperature known as the boiling point, which is unique to each pure liquid. Freezing is when a liquid changes to a solid. This is a reverse of melting and occurs exactly at the same temperature as I stated before. Hence, the melting point and freezing point of a pure substance are the same. Water freezes and melts at 0 degrees Celsius, which we all obviously know. Requires a significant decrease in temperature and occurs at a specific temperature. Yes, we looked at that. Evaporation. It's when a liquid changes into a gas. Evaporation only occurs at the surface. Now that's a key difference. Evaporation only occurs at the surface. Boiling occurs throughout the liquid. Where high energy particles escape from the liquid surface at low temperature below the boiling point of the liquid, the low energy particles then remain in the liquid. The larger the surface area and warmer the liquid, the more quickly a liquid can evaporate. And for most liquid, evaporation occurs readily over a range of temperatures without needing to heat the particles at the surface. Absorb heat from the surroundings. The addition of heat will just accelerate the process, and boiling occurs if the temperature exceeds the boiling point of liquid. For example, water can boil from around 80 degrees to, let's say, 99, and then once it crosses 100, then it starts to boil. I'm not sure, I'm just guessing this once. Please, I'm not sure before you comment and tell me I'm wrong. Then we have condensation, when a gas changes into a liquid, usually on cooling. When a gas is cooled, its particles lose energy, and when they bump into each other, they lack energy to bounce away. So this is how the gas particles are. Then when they bump into each other, they no more have energy left, and that's why they stay like that. No energy is required for condensation to occur. It takes place over a range of temperatures, just like evaporation. Sublimation, it's when a solid changes directly to a gas. That only happens with a few solids such as iodine or dry ice, which is also solid carbon dioxide, CO2. S stands for solid. The reverse reaction also happens, yes, deposition or desublimation occurs at a specific temperature unique to each pure substance. Yes, this arrow means it's a reversible reaction. Don't worry, reversible. Don't worry, it will be taught in grade 9 and the videos will come on it. Read the question, blah blah blah. We don't look at that. We skip. Gaseous particles. Gaseous particles are in constant and random motion. An increase in temperature increases the kinetic energy of each particle. As the thermal energy is transferred to kinetic energy, so they move faster. Decreasing the temperature has the opposite effect. The pressure that a gas creates inside a closed container is produced by the gaseous particles hitting the inside walls of the container. As the temperature increases, the particles in the gas move faster, impacting the container's walls more frequently. This increases pressure. So what do we know? As temperature increases, pressure increases. As temperature decreases, pressure decreases. That is that. Then we have diffusion. Diffusion occurs in only fluids, does not occur in solid. Fluids are basically liquids and gases. This is the process by which different gases or different liquids mix, and due to the random motion of their particles. Really important. Diffusion, the particles move from area of high concentration to area of low concentration. Eventually, and remember, no energy is required for that. The concentration of the particles will become even. So what happens is that, let's say, okay, we have given an example. We have particles at this end of the container, so, and we have very few particles, let's say. So these particles will move out until it becomes even, like this. Okay, let me give a proper example. Diffusion of potassium manganate. Potassium manganate is pink purple in color. After a few hours, the concentration of KMnO4 or potassium manganate 6 is the same everywhere in the solution. So at first we have our potassium manganate here. It starts to diffuse due to its random motion. It starts diffusing outwards where there's low concentration. It's moving outwards because there's a fewer or lower concentration of potassium manganate, or no concentration, we can say, over there. So it fails to occupy the space, and after some time it fills the entire, it's even, the particles are evenly spread. Yeah, okay, let me write that properly. And this is the graph. So we have our high concentration over here. The concentration tends to decrease as its position increases. So we have A, B, C, D. As its position increases, its concentration, which is very high over here, becomes low over here until it finally reaches 0, and then it's spread evenly. Then we have changes in state and the kinetic theory. It's really important to know the kinetic theory, so please pay special attention here. When substances are heated, the particles absorb thermal energy, which is converted into kinetic energy, and this is the basis of kinetic theory of matter. So the particles absorb the thermal energy, let's say using a Bunsen burner, which is used to heat an object. To heat an object, it will absorb the thermal energy from the Bunsen burner, convert it to kinetic energy. That's kinetic theory of matter. Heating a solid causes its particles to vibrate more, and as the temperature increases, they vibrate so much that the solid expands. They break their bonds until the structure breaks and the solid melts to a liquid. On further heating, the now liquid substance expands more and breaks the bonds of its liquids and forms a gas. When the boiling point temperature is reached, all the particles gain enough energy to escape and the liquid boils. This can be represented on a heating curve and a cooling curve. So so let me just tell you before we start. Heating curve and cooling curve are exactly the opposite. While the heating curve goes up, the cooling curve comes down. So we have our solid. Temperature increases, time goes forward. So a point comes at which solid changes to a liquid, and the temperature remains the same because energy is required to break the bonds of solid to form a liquid. Remember that the question may come, why is this line straight? Because a pure substance is being used. Or how do you know that a pure substance is being used? So you basically say the line at the melting point is straight. Then the same continuous liquid, particular time is required to break the bonds in liquid to form a gas, moves ahead, the time passes, then it forms a gas, then it has no effect. Similarly, the same happens in cooling curve. We have our gas here, then it as temperature decreases, the particles come together and lose energy so that they are no longer able to move apart. Changes to a gas, liquid changes to solid, and solid changes to liquid changes to solid, and solid is there. Evidence of particle movement in matter. Now, how many of you use perfumes? If you use perfume, when you put perfume, and then, like, how do I say it? When you put perfume, don't people compliment you? hey, you're smelling really nice, or your mother tells you you're smelling really nice and all of that, is because let's say you are here, you have put the perfume, because you have high concentration of perfume here and low concentration of perfume outside, the perfume starts to diffuse outside. And let's say your mom is standing here, so she smells the perfume and compliments you. I know it's a very stupid example, but then use it as a way to remember it. That's my way. Example: spread of odors, perfume, petrol, smoke particles. And diffusion rate depends on several factors. These factors include the mass. The heavier the mass, the slower it is. The lighter the mass, the faster it is. Temperature: the higher the temperature, the faster it diffuses. Presence of other substances: the fewer the particles there, the faster the diffusion. And intermolecular spaces: the less intermolecular spaces, the faster they diffuse. That's why gases diffuse faster than solids, and solids do not diffuse because they have a very strong intermolecular space. Now, this is a question that is definitely going to come when your teacher is teaching you this. You will be giving NH3 and HCl, and they'll ask you, it's a gas, so it moves this way, and this one is moving this way, and when they form, a white cloud is formed. At which position will it be formed? A, B, or C? The correct answer will be C, but make sure that the HCl is on this side, and the NH3 is this side, or sometimes this could be here and this could be here. But instead of memorizing it, let's get to know why that is so. So let's find the molecular mass of NH3. N is 14 plus 3, 1. This is 17. H is 1 plus chlorine is 35.5. That's 36.5. So we know that hydrochloric acid is heavier than ammonia, which is why it will move slowly to this point, whereas this will move fast all the way, and they will react here to find the white cloud. That was just the experiment. Another experiment is we have bromine gas at the bottom, and then we cover it. Then as soon as we open it, after some time it will spread all over. High concentration of bromine, very less concentration, it diffuses upwards. This experiment states that diffusion not only happens right or left or up or down, it happens in all directions. Then diffusion in liquids, we looked at diffusion in liquids in the potassium permanganate question. But another experiment we could do is take a bowl and add some water to it. Then take a drop of ink and pour it from the top. You'll see that the ink diffuses, making the whole water the color of the ink, let's say blue. At first the water is watercolor, and then after some time, after adding the ink, you'll see that the water becomes blue because the ink has diffused all over. And that'll be all for today's video. I hope you learned something new. If I made any mistake, please feel free to correct me in the comment section. If you learned something new, if the video helped you, please make sure to subscribe, like, share. See you in the next video. Till then, ta-da.